All right, welcome Physics C students to Electrostatics Notebook Part 2. We're going to cover electric fields today. So first, we're on page 82 here. You can define electric field, the magnitude of the electric field, and the direction of the electric field by doing some research on your own. Check several sources. I've put a word bank here that you can use. You can certainly use more words than that, but those are kind of a good list to start with. So pause the video here, do some research to find those on your own, and we will check those in class. So pause and then continue when you're done. All right, so hopefully you researched those on your own. We're going to continue on here. For a point charge, the electric field is the force per unit charge in magnitude. And if we take the Coulomb's law for force, we get K Q1 Q2 over R squared, and then we're dividing by another Q here on the bottom. Now, this Q that's on the bottom right here could either be charge 1 or charge 2. It doesn't really matter how you think of it. I'm just going to say that's charge 2. Those will cancel off, and we would get KQ over R squared. And that is the magnitude of the electric field from Q at a distance R away from the charge, right? So it's very similar to Coulomb's law, it just doesn't have both of the charges up top. Again, think about the magnitude and the direction separately. The direction of the electric field is the direction a positive test charge would go if put at that point in space. Positives get repelled by positives, and positives get attracted to negatives. So for a positive, we can see here that the electric field is stronger when we're closer. It dies off as we go further. If we go from 1R to 2R, then we have 1/4. If I go out to 3R, I'll have 1/9 of the field. That's the inverse square part of it. And we can see that for this positive charge, the electric field points away because that's the direction another positive charge would experience a force. So the electric field points away from a positive. And here, the electric field will point towards a negative charge. All right, on to the next page. We got an example that we're going to look at. We're going to use the principle of superposition. Superposition means that the net effect is equal to the sum of the individuals. Right? So we can add up the individual electric fields to find the net electric field. That's the idea of superposition. So in part A here, I'm going to draw a number line. And I'm going to mark off 0, +3, -3, and then I'm going to have a charge of Q here at -3, and over at +3, I'm going to have a charge of 9Q. We should think about the direction that the electric fields point. Electric fields point away from a positive. The electric field from 9Q is going to go that way. It's going to go that way. And it's going to go that way. And the electric field for Q is going to go that way. that way, and that way. So we can see here that the E fields add when x is less than -3 or x is greater than 3. And because we're adding together the fields, essentially it's going to make the field stronger and it's not going to cancel out. The E fields will cancel, or at least they'll subtract. Right? Maybe that's a better word of saying. They will subtract between -3 and +3. And if we think about the magnitudes of the fields, when we're closer to a charge, we have a bigger field. When we're farther away, we have a smaller field. So if we were right in the middle, the field from 9Q would be bigger because we're at the same distance. So what we need to do is move closer to -3 so that we're closer to the smaller charge, and that makes up for being, the larger charge will be at a greater distance, and that makes up for the fact that it's larger. So we can summarize that by just saying that E equals 0 closer to x equals -3 than x equals +3. We don't need to go and figure out exactly where it would equal 0. We're just kind of doing this conceptually right now. In the next example, we have the same number line with the same size charges on it. So here we have Q, but now the charge over at 3 is now -9Q. And the difference is that a electric field points towards a negative. So the electric field from 9Q is going to look like that. And the electric field points away from this positive still and away. So what do we have here? Well, we have that the electric field will add, between -3 and +3. So that it's not going to equal 0 in that region because they add together because they are facing the same direction. What about out here, over on the right? Well, over here, they do subtract, they will cancel, but we're always going to be closer to the larger charge. And if we're always closer to the larger charge, the electric field from the 9Q is always going to be larger than the electric field from the single Q. And while they will subtract, they won't ever totally cancel each other out. I'm just going to say that the E fields cancel for x is greater than 3, but the larger charge is always closer. So E cannot equal 0 in that region, which leaves us only the region on the left of -3. And we can say there that the E fields cancel when x is less than -3. And we can even say that E equals 0 at x equals -6. And if you think about what we would have there, we'd have a field from the Q charge of negative KQ over 3 squared. Why do I say 3 squared there? It's because negative 6 is 1, 2, 3 charges, or 3 units away from negative 3. 1, 2, 3, and that's where that 3 comes from. It's the difference between negative 3 and negative 6. Right, so it's the distance away we are from Q. And for the 9Q charge, we're 1, 2, 3, 4, 5, 6, 7, 8, 9 charges away. And notice that that field is to the right, so I made it positive. And this field from Q was to the left, so I made it negative. So for the 9Q charge, we'd have K times 9Q over 9 squared. And if you think about what these will simplify to, we're going to have, this is basically KQ over 9, and this is 9KQ over 81, and 9 over 81 reduces to 1/9, so they will cancel out and we'll get 0 field. In the next example, we're going to calculate the magnitude and direction of the electric field at point A. And remember, the electric field for a point charge in magnitude is KQ over R squared. And if we go ahead and define, like, this could be charge number 1, Q1. And at the origin, a negative charge, it's going to have an electric field in this direction. So that'd be like E1. And then we can say that this charge here is Q2. And a positive, the field goes away. So that would be E2. And then this charge, we'll call that Q3. Again, it's positive, so its electric field is going to go away. E3. We have 2 fields to the left, 1 to the right. We will add those up. The ones to the left will be negative. Right? So these ones will be negative. This one will be positive. And we're going to have E1 plus E3 minus E2. And that's going to give us K. Remember, we can, since K is common to all of them, we can take it out front. That's 9 times 10 to the 9th times, and we're going to have a negative, and this would be Q1 over R1 squared. And then we'd have a, oops, I made a mistake back here. E1 here should be negative. E3 should be negative, and then E2 should be positive. We've got negative E1, and we're going to have a minus. Again, this would be like Q2 over R2 squared, and then we'll have a plus and you can put those all in your calculator. You'll fill in the numbers, put that all in your calculator, figure out how many newtons it is, or sorry, how many newtons per meter. Not newtons per meter, newtons per coulomb. Sorry, force per unit charge. Force newtons, charge coulombs. So it's in newtons per coulomb. Then in part 2, what's a simple formula we could use to estimate the net electric field at a very large distance? Well, we would just basically use KQ over R squared, but Q is going to become the net charge. So you'd add up the three charges. You'd find the net charge, and then x is just the distance we are, and we could approximate these charges as just being at the origin. They'd actually, be a little bit to the left of the origin if you were to average them out, but at very large distances, hundreds, thousands of meters, a couple meters is not going to make much of a difference. So for an approximation, kq over r squared will work anytime you're a far distance away from a arrangement of charges. Then in the next example, you're going to do a calculation for the electric field at point P. Now I'm going to call this charge up on the top charge number 1. I'm going to call this charge on the bottom charge number 2. This distance right here is A. That would also be distance A right there. I'm going to define this angle to be theta. That's the same as that angle. This length here, r, would be the square root of a squared plus x naught squared, and this is x naught here. So we made a triangle there. It's the hypotenuse of the triangle. And since both of these are positive, the electric field is going to point away. So I'm going to have the electric field from number 1 point that direction. The electric field from number 2 points that direction. And the net electric field points that way. The vertical components of these two electric fields cancel out by symmetry. Only the horizontal component is going to remain. And in part A right here, E1 in magnitude equals kq over r squared, which is going to be kq over a squared plus x naught squared, which is r squared. That's this r squared on the bottom. And that will also equal in magnitude E2. The net electric field is equal to E1 in the x direction plus E2 in the x direction, which is going to equal 2 times kq over x naught, keep it, a squared plus x naught squared times, and if I just want the x components, there's going to be angle theta as well. If I just want the x component, I'm going to take cosine of theta. But we know that cosine of theta is adjacent over hypotenuse. And adjacent to this angle is x naught, and then the hypotenuse here. So I take adjacent, x naught, and the hypotenuse was the square root of a squared plus x naught squared. So our net electric field is going to be 2 kq. I'll have this a squared plus x naught squared on the bottom, and I'm multiplying that by x naught over the square root of a squared plus x naught squared. And if I just simplify that one more time, I'm going to get 2 kq x naught over the quantity a squared plus x naught squared all the 3/2 power. 3/2 power because this is really to the 2/2 power, and this is to the 1/2 power, right? So this would be like to the 2/2 power, this is to the 1/2 power, and then when we add those exponents, we get this 3/2 here. Last part of this is show that it's sufficiently large distances, we can use kq over r squared. So as x naught gets larger, we could say as it goes to infinity, or we could just say as it gets larger. Because we're not going to go all the way to infinity. So as it grows larger, x naught becomes much, much bigger than a. And x naught squared plus a squared will approximately become x naught squared. R will approximately become x. And so we'll get that E, which was 2kq. Actually, I've got it written right below. So that's the answer for part 1, but then we can say here E becomes approximately, and on the top of this, we're going to have 2kqx, and on the bottom of this, we'll have x naught squared to the 3/2 power, and that basically becomes 2kq over x naught squared. Why x naught squared? We had an x up here. This is going to become x to the 3rd, and then the x and the x cancel, and we're just left with 2 of them. And that is basically kq net, because q net was 2q, right? And on the bottom, x is the same thing as r. All right, that's going to set us up for the next video. I'll make 2 smaller ones this time. And in the next video, we'll talk about ways that you can draw the electric field.